It's an alien landscape where magnetic tornadoes twist upward tens of thousands of miles. Mysterious dark spots, large enough to engulf the Earth, ebb and flow. And violent eruptions shoot tons of charged particles into space at speeds of over 2 million miles per hour. This is not some strange world on the other side of the galaxy. This is our sun. And now, new technologies are allowing us to see it like never before. Satellites are giving investigators new insights into centuries-old mysteries.
Whoa, did you see that?
Boom, there goes a flare.
That is really a quantum leap in solar physics, a continuous eye on the sun.
How does our sun work? Where does its power come from? And how can its inner workings impact us some 93 million miles away? Finding answers has a new urgency.
Before the expert by about 68
And the bigger hit.
The bigger hit.
Our sun has a dark side. Its violent storms capable of taking down the electrical grids that power our daily lives.
Repair could take weeks, months, and even in a worst-case scenario, up to 10 years for a full recovery.
If you can imagine a world without electricity, you're really going back in time.
Now, join scientists on a quest to understand the secrets of the sun. Dive deep into its core and ride out its spectacular storms. Right now, on this Nova National Geographic special.
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science.
Discovering new knowledge. HHMI.
And by the Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you.
Dawn, February 15th, 2011, Boulder, Colorado. The team at the National Space Weather Prediction Center begins its day as it usually does, carefully watching the surface of the sun.
Okay, a 10 centimeter came in today.
Although 93 million miles away, forces here can impact Earth in surprising and destructive ways.
For the smaller,
The M6.
for the M6, you see this, the very first one is the M6.
Today, after years of relative calm, a satellite detects something. A dramatic explosion on the sun's surface. A violent solar storm that would dwarf Earth is erupting, releasing a massive shockwave, hurtling towards us at over 1 million miles an hour. Right now, no one is sure what to expect.
But I think that the M6 is going to get here.
We have to determine when that thing is going to impact Earth's magnetic field.
8 hours.
It's going to be sometime tomorrow, perhaps later in the morning, later at night. That's exactly what we're trying to determine. In fact, I have to join the discussions right now, so I'll get back with you.
The team models the approaching storm.
So 15Z for the arrival of the CME. This is it here.
Right
okay.
there.
Their simulation shows it racing out from the sun on the left towards the small dot on the right,
So we're looking at about
Earth. The solar storm carries a 1-2 punch. First is a solar flare, releasing an outburst of X-rays that can reach Earth within minutes. The second, more ominous threat arrives a few days later, a phenomenon called a coronal mass ejection, or CME. It's a wave of billions of tons of electrically charged particles, seen here in this repeating image as it ripples away from the eye of the storm. Together, they could hit like a cosmic tsunami. Delivering a surge of radiation and an electrical spike of trillions of watts, potentially crashing the power grid. Sound far-fetched? In March 1989, in Quebec, Canada, that's exactly what happens. One by one, power stations crash, disabled by the overwhelming power surge caused by a CME wave. In less than 2 minutes, 6 million people are left without power. Recently, NASA's Jim Green finds evidence that an even bigger solar storm hit Earth in 1859.
And what we found was the granddaddy of geomagnetic storms, and that was just 150 years ago.
If we had a geomagnetic storm of that intensity today, the National Academy suggested that the impact on critical infrastructure could be catastrophic. And the big concern is the electric power grid.
The massive electrical surge from a CME wave could overload power lines and melt transformers, blacking out entire cities.
Repair could take weeks, months, and even in a worst-case scenario, the National Academy suggested up to 10 years for a full recovery.
If that occurred, if you can imagine a world without electricity, you're really going back in time.
It's not just the power grid that's at risk.
More and more, we rely on technology that could be affected by the sun. Global positioning satellites, long-distance communications, airplane tracking, astronauts in space.
Roger, how does it look?
So there's an urgency in understanding what it is that the sun is doing, what's it going to do next, and how can we prepare for that and respond to it.
Worried or not worried?
Well, I would be just a little bit worried, given concern right now. We'll be watching it, monitoring it very closely here in the coming days.
We've gazed at the sun since antiquity. We've worshipped it and built entire cultures around its power. We marveled when it's eclipsed during the day. And when its power lights up the night sky with dancing curtains of light, the aurora. Its power and size are awesome. It is so huge, 1 million Earths could fit inside it. Temperatures at its core soar to 27 million degrees Fahrenheit. It's been shining for over 4 billion years, and will do so for at least 4 billion more. Yet for something that has such an overwhelming influence on our lives, the sun is mysterious. How does the energy generated in its core reach us as sunlight? What processes are at work inside the sun? How do these powerful inner workings generate explosive solar storms? These are some of the mysteries scientists must understand to protect us from the sun's darker side.
The sun can really surprise us.
The sun is elusive,
Crazy,
Complicated.
crazy,
Incredibly dynamic.
crazy.
With explosive potential.
The key to that explosive behavior lies deep beneath the sun's blinding surface. Until recently, seeing inside the sun was impossible. Understanding its internal processes, a pipe dream. But an accidental discovery changes everything.
Until the 1960s, much of solar physics relied on things that were like solar dermatology. It was things that were right at the surface or just skin deep.
But as physicists study the sun in more detail, they make a surprising discovery. The surface seems to be vibrating, like ripples on a pond. Initially, they think the vibrations are the result of defective instruments.
They couldn't get rid of them. They built better instruments, the ripples were still there. They looked at it for 10 years, and they conferences, they all talked about it, and they harumphed. But what it turned out to be was just sound waves.
It is an astonishing revelation. No one expects that the sun can generate sound waves. It leads scientists to see the sun in a completely new way. Our sun vibrates like a giant pipe organ. But instead of air producing the notes, churning gases deep inside send sound waves rippling through its interior.
Because a sound wave changes as it moves through different material, we can look at the different frequencies and determine what's happening inside the sun.
Geologists are familiar with this. By studying sound waves passing through the Earth's crust, they can see the layers below our feet. A technique called seismology. Similarly, sound waves moving through the sun's interior reveal how it's made up.
I can use this organ to illustrate how sound waves work inside the sun. For example, if I hit this low note, it comes from under these big pipes, big deep sound. And on the sun, that corresponds to a wave that goes very deep into the sun and brings back the information from deep down in the sun. If I turn to a high note, it comes from a much shorter pipe, and on the sun, that's telling us information about very close to the surface of the sun, not very deep at all into the sun.
There are 10 million different frequencies resonating in the sun. Deciphering them leads to a seismic shift in understanding its structure, creating a new science, helioseismology.
Once the helioseismology came along, we could not only see what the surface was, but we could actually tell what the physical processes were underneath. So by looking inside, we can actually see what the sun is doing.
It is a powerful tool to see beneath the sun's surface. Studying the sun's sound waves reveals a complex, multi-layered machine. Directly beneath its blazing surface is a zone of perpetual churning. Next is a layer where light takes thousands of years to cross. At the center is the sun's core. It's the smallest region, but it's over 25 times the diameter of Earth. This is the powerhouse of our star. Everything we experience on Earth, sunlight, heat, and the effects of solar storms, starts here. So what's it like here? What's the core made of?
Well, the sun's a crazy place, right? It's far too hot to be a solid. We know that. Right? Heat it up, it's far too hot to be a liquid. And so you think, well, it's a gas, right? Well, not really. It is this gaseous soup of charged particles that we call plasma.
You're more familiar with this soup than you might think.
There are plenty of examples. Fluorescent light bulbs, flames, neon lights, perhaps fancy TVs that I can't afford, but these are all plasma. Plasma is sort of all around you.
But plasma is radically hotter at the sun's core. The closest thing on Earth is lightning. During thunderstorms, electric charges build up, creating lightning bolts that reach tens of thousands of degrees.
That's pretty hot, but it's nowhere near as hot as in the core of the sun. So if you were to travel into the core of the sun, the plasma would be 15 million degrees.
As the sun formed, hydrogen gas at its heart was crushed under the weight of the material above. Eventually, temperature and pressure rose so high, the hydrogen atoms broke apart into electrons and protons, creating plasma.
And it's under these extreme conditions that something really, really cool happens. Nuclear fusion.
It's the same atomic process inside the hydrogen bomb. Under tremendous pressure, protons in the plasma fuse together, releasing photons, minuscule packets of heat and light. An unimaginable number of photons are made every second, generating the sun's incredible power, some of which reaches us as sunlight. This atomic alchemy converts over 4 million tons of mass into energy every second in an endless loop.
That much mass into energy is the equivalent of 10 billion hydrogen bombs being created every second. The sun does this day in, day out. It's been doing it for 4 billion years, and it's going to continue to do so long after I'm gone.
The energy of billions of bombs is released in the core every second. This begs a simple question.
So you could ask, well, why doesn't the sun blow itself apart? It's because there's this beautiful balancing act that occurs. In the core of the sun, you've got this pressure from all of this fusion pushing outwards. And the sun is huge, so you have all this gravitational pressure pushing downwards. And so you've got gravity pushing down, and the sun trying to blow itself apart from the inside, and it is this beautiful balancing act between the two that keeps the sun in one piece.
This light, born at the core, reaches us after a remarkable journey. Away from the core, pressure and temperatures drop, and nuclear fusion stops. Now, each photon begins a tedious journey through the sun's thickest layer of plasma, a region called the radiative zone. Although squeezed less than at the sun's center, the plasma is still very dense, and photons struggle to move through it. Each packet of energy is continuously absorbed, then spit out by the plasma particles.
In that particular part, there's no energy being generated, but the energy is transmitted by the radiation. So that's why we call it the radiative zone, not too surprisingly.
The photons slowly bounce through the plasma here, ricocheting in a zigzag path called the random walk.
So imagine that you're in a crowded room and you're trying to make your way through and you greet other people. And each person you greet, you have to say hello to, and then you move off in another direction. So it takes you a long time to get from one place in the room to another because you're just kind of meandering your way around the room. So the same way the photons in the inside of the sun, they don't have a preferred direction. All they want to do is they want to be moving and they want to be greeting other particles.
Though moving at the speed of light, 186,000 miles a second, it takes photons over 100,000 years to cross the zone. Eventually, the photons reach a boundary where pressures drop again. The plasma thins, and moving through it gets easier. The photons still pack a lot of energy. Now, they leak out into the convection zone, heating it from below. The thinner plasma in this zone makes the photons move in a different way.
So instead of bouncing, all of a sudden there's an ordered motion. So it's as if all of a sudden someone said, lunch, and all the particles decided, oh, we all have to go this direction. You still have to wait in line to get out, so it takes a month to get from the bottom of the convection zone to the surface, but it's a relatively short period.
During this short period, heat from the photons sends plasma here into perpetual motion, a maelstrom of churning 125,000 miles thick. Think of it like a massive lava lamp.
There's heat that enters at the bottom from the light bulb. It heats the material and the blob rises to the surface. When it gets to the top, it cools off. And when it cools, it gets more dense and falls back down. This is a good analogy for what's happening inside the sun. We have the core of the sun heating the material at the bottom of the convection zone. The material expands and it carries the energy upward until it gets to the surface.
These incredible images reveal convection at the sun's surface, rising and sinking plasma that creates a mesmerizing structure called granulation.
The granulation cells are about the size of the state of Texas. They only last for about 12 minutes, so there's an incredible amount of energy. It's a very dynamic, very chaotic place. And all of the activity is going on the surface of the sun where we can see it.
Photons produced at the core finally reach the surface. They emerge as a weakened form of solar energy. This weakened energy reaches Earth in 8 minutes. We know it as sunlight.
So 100,000 years, about a month, and then 8 minutes. Once you get to the surface of the sun, it just takes 8 minutes to get to where you can see it.
Unimpeded, the trip from the core to the surface would take the photons a matter of seconds. In reality, the sunlight that shines on us today may have been created during the last ice age. Energy reaching the sun's surface doesn't just result in sunlight. It can also trigger solar storms. Understanding the sun's destructive power requires 24-hour precision surveillance, something that, until recently, was impossible to achieve.
5, 4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were going to open our doors that actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed a portion of the sun in high resolution. Now, they see it in mind-boggling detail.
Now, in order to look at the Solar Dynamics Observatory images that we're bringing in every day, we've built this very special wall, which is 9 high-definition television screens together that can display these images, so that the instrument and the display system together are an entirely new way of looking at the sun.
We can see all the details of what is going on, and that is really a quantum leap in solar physics. Being able to see all of that all the time, a continuous eye on the sun.
One of the most important aspects of SDO is its ability to see sunlight across a range of wavelengths, the equivalent of looking at things glowing at different temperatures. Our eyes are most sensitive to sunlight glowing at around 10,000 degrees Fahrenheit. At this temperature, the sun's surface looks almost featureless. But at hotter wavelengths, normally invisible, a far more dynamic picture emerges. The February 15, 2011 storm is a perfect example. In this repeating image, at around 90,000 degrees Fahrenheit, SDO captures just a ghostly trace of the CME wave. But at just over 1,000,000 degrees, the superhot plasma rippling away from the eye of the storm is much clearer. This allows researchers to see coronal mass ejection waves evolving across the entire sun.
This is an absolutely amazing time for solar physics because of these beautiful high-resolution images that allow us to understand better the physics behind what's going on when solar storms erupt.
There's that one last photo. Look at this one.
Back at the National Space Weather Prediction Center,
That's the M1 here.
Bill Murtaugh tracks the storm's CME wave. It carries 1 billion tons of plasma and is now only about 20 hours from Earth.
We're bringing it in mid to late on the 17th into the 18th.
What they see is alarming.
Well, there's actually 3 CMEs that we're looking at. So we bumped up some numbers for late tomorrow. Yeah.
It's not a single CME wave, but 1, 2, 3 of them.
We won't call it the perfect storm yet or anything, but conditions are lining up for some significant space weather.
Their models show trajectory and speed, but the big unknown for Murtaugh is how powerful the waves will be when they hit. The answer lies in a force that governs the sun: magnetism. We're all familiar with magnets. They produce an invisible force that pushes and pulls on charged particles. In fact, Earth has a magnetic field that protects us against threats from the sun. But we are less familiar with the sun's magnetic power, which researchers believe plays a major role in driving solar storms.
We've essentially learned that it takes two things to make a star magnetic. It needs to have these convective motions right underneath the surface, the bubbling of the gas. It needs to spin, and the faster it spins, the more active it becomes. And wherever those two things, the bubbling and the spinning, can interact, that's where we see the strongest magnetic activity in stars.
Astronomers know that the surface of the sun spins in a strange way. Travel from the poles of the sun towards its equator, and you'd notice it turns faster. Analyzing sound waves inside the sun reveals that the plasma layers beneath the surface also spin at different speeds. That's because they act like fluid, which gets denser towards the core. The interior of the sun is a place of spectacular turmoil. Turmoil that's the key to the sun's magnetism.
The motions there, the convection, the differential rotation, the motion from equator to pole, are driving a new force. They're driving a magnetic field. There's a dynamo at work here. A dynamo that's generating a force that we actually experience here on the Earth.
It works like a giant wind turbine. Churning plasma in the convection zone stirs up powerful electrical currents, which generate a huge magnetic field.
Have upflows here and downflows coming down this way, right?
The holy grail for scientists is understanding exactly how this dynamo generates solar storms. The clue lies deep within the convection zone. Magnetic field lines normally run from pole to pole. But with all the turmoil in the convection zone, that's generating a magnetic field. The field lines wind up to the point that it explodes in a solar flare. Now, SDO provides a complete and unprecedented picture as these events evolve.
This is beautiful because the hot gas outlines the magnetic field lines that we would otherwise not be able to see. And here you can see even a twisting structure as some of the mass drains back down to the surface, and a lot of it escapes in the eruption. This is the essence of space weather, or solar storms.
This explains how flares form, but it's not the end of the story. Crossing magnetic field lines can cause nets of plasma to be flung into space. This is a coronal mass ejection, a CME wave. The portrait of how solar flares and CME waves form is coming into focus. But a key question remains. CME waves can travel 93 million miles to Earth in a matter of hours. So what gives them such explosive energy? Part of the answer is hidden here in the sun's atmosphere, the corona. It's made of superhot plasma that blisters at over 3 million degrees Fahrenheit. 300 times hotter than the sun's surface. Some scientists suspect that this heat powers massive gusts of energy that blast CME waves toward Earth at incredible speeds. But why the corona is so hot is an enduring mystery.
Understanding it's essential if we want to get to the bottom of how the sun drives space weather and the impact of the sun on the Earth.
The fact that the corona is so much hotter than the surface flies in the face of physics.
The sun's corona is a very odd place. Take this fire, for example. As I put my hands close, sure, it's warm, but as I pull them away, it gets cold. That's not the case on the sun at all. As you go in close, it's definitely warm, but as I pull away, it actually is warmer still.
Recently, Japanese investigators observe high-velocity jets of plasma shooting up from the near surface. McIntosh suspects these jets deliver heat to the corona, but he doesn't have a way to confirm it visually until he turns to SDO for help.
Lo and behold, we actually managed to join the dots and see, yeah, these objects that we could see moving out of the lower atmosphere at high speeds, kind of like these licks of flame, really were reaching a couple of million degrees. It was really a tumultuous moment. We kind of looked at each other and said, wow, what have we just done?
They've shown that the plasma jets accelerating upwards from near the sun's surface generate tremendous heat. As a result, temperatures in the corona soar to 3.5 million degrees. If confirmed, it represents a huge leap forward in understanding CME behavior. The immense heat of the corona acts like a wind in a raging gale. It's constantly pushing on the plasma draped on the field lines, billowing them out like sails pulling on a mast. Like solar flares, when magnetic lines cross, there can be an immense explosion. In this case, the lines are cut and the sail whips off into space. Loaded with 1 billion tons of highly charged plasma, the CME wave can wreak havoc on electricity-dependent Earth. At the National Center for Atmospheric Research, this violent event is captured by satellites.
Now, to see the CME, we need to create a little artificial eclipse. To do that, we block out the light from the disk of the sun, and that's this little circle here. But what that allows us to do is to see this extremely faint, high-speed thing shooting away from the sun. This one moves at about 1,000 kilometers per second.
By enhancing the picture and slowing it down, it's possible to see the shockwave moving at over 2 million miles per hour. Though we have a better understanding of what causes solar storms and how they reach us, there is still a final pressing problem.
Trying to predict when solar storms are going to occur on the sun really requires a lot of detective work. Basically, we're looking for clues in observations to tell us when potential storms might occur.
The best clue comes from these. Sunspots. Dark patches which can linger on the sun's surface for weeks at a time.
A sunspot is a massive region, several times the size of the Earth, which appears on the sun as a dark spot. It's dark because it's relatively cool compared to its surroundings. And it's cool because the magnetic fields are so strong that they're suppressing the flow of heat from below.
The strong magnetic fields which create sunspots are the breeding ground for solar storms. The challenge is trying to decipher a pattern for when and how many will appear.
As we watch sunspots over a period of many years, we see something very interesting. The number of sunspots at any given time will wax and wane over a period of about 11 years. And since we now know that sunspots are associated with strong magnetic fields, this tells us that the sun's magnetic fields are likewise going through a cycle.
The constant churning and twisting inside the sun creates a powerful dynamo, the biggest electrical generator in the solar system. The magnetic field lines it produces get so wound up that roughly every 11 years, the magnetic poles of the sun reverse. After that, calmer magnetic activity prevails and fewer sunspots form, a period called solar minimum. But because of the sun's turbulent nature, the field gradually winds up again. As it does, magnetic outbursts are far more common, a period called solar maximum.
The solar cycle actually determines the personality of the sun. During solar maximum, it can get very angry and it can throw off solar storms that are sometimes directed at the Earth. And during solar minimum, it becomes much more subdued. There aren't as many sunspots, there aren't as many solar storms occurring. The activity cycle basically determines how the sun is going to act.
Prior to the solar storm of February 15, 2011, things were pretty quiet on the sun. But that outburst marks an ominous turning point. The sun's magnetic activity is winding up again as it heads towards solar max. Just a few days ago, Bill Murtaugh and the team at the Space Weather Prediction Center witnessed the turn.
Arrival of the X2 and the M6, if it comes in with any geoeffectiveness, between 12 and 1800.
So that's what we're seeing.
It's now time to let the world know what it might expect.
Nothing higher than
In the next couple of minutes here, we're going to have to make a decision and make the prediction that this coronal mass ejection is going to arrive at whatever time tomorrow, and the geomagnetic storm will ensue, of course, once it arrives.
With the event we had...
Murtaugh knows that the severity of the storm depends mainly on two things: how strong the CME's magnetic field is, and at what angle it hits Earth's own magnetic field. CME waves approach Earth like a slowly rotating shield. One end is positively charged, the other negative. With magnetism, opposites attract, and like poles repel. If the wave's positive pole lines up with the Earth's positive pole, most of the power of the storm will be repulsed. But if opposite poles line up, the plasma the waves are carrying will hit with full force.
Did you say it came in at 115?
114.
Murtaugh makes his final assessment only hours before impact.
It will be larger, more complicated, typically, than just your single coronal mass ejection.
I think we nailed the forecast.
Okay. I'd like to think so.
According to the observations, the CME wave will be repelled.
We don't expect it to be too strong. We'll see moderate storming levels, which is good enough to produce some aurora borealis down in the United States, down along the Canadian border, northern tier states, and it will cause some minor problems to the power grid and whatnot.
Space weather for the next 24 hours is expected to be minor. Radio blackouts reaching the R1 level are expected.
This time, we dodged a bullet. But disturbing evidence suggests the Earth will not always be so lucky. It's a cautionary tale. NASA's Jim Green discovered it while researching a book on the American Civil War at the Library of Congress. Green found news accounts from 1859, which caught his eye.
I would run across articles about aurora, fabulous aurora. And this really piqued my interest because it's in my field. It seemed as though the armies of heaven were engaged in terrific, though noiseless, conflict. This terrific aspect soon subsided into a more beautiful and brilliant appearance, a few of which I can only refer to.
The reports tell of auroras so bright, miners in Colorado wake up and go to work thinking it is dawn. Other accounts tell of a more harmful impact on the lone electrical system of the day, the telegraph.
One, for instance, because of the induced current on their system, overheated the battery and started a fire, nearly burnt down the telegraph office. Another operator was burnt so badly he ended up into the hospital.
Green uncovers numerous reports of auroras seen not only across the United States, but around the world. The evidence is clear. Earth was struck by a superstorm in 1859, the result of two massive CME waves.
Those two storms were not only enormous, but they happened one right after the other. No one alive has seen anything like it.
On the day before the waves hit, a British astronomer observes a giant sunspot group light up with two massive flares. The second CME wave hit 18 hours later, allowing Green to calculate its speed, 5 million miles an hour, plowing into Earth at almost 4 times the speed of the February 15, 2011 CME waves. Using the various reports, Green is able to reconstruct the 1859 storm. The accounts suggest that the poles of the CME waves were aligned, and instead of being repulsed, the waves hit with full power. The charged particles funnel down into the atmosphere, electrifying it like a giant neon sign, producing dazzling aurora displays. The storm is so intense, Earth's magnetic field all but collapses. Millions of tons of plasma spill towards the equator, and a powerful electric surge pulses over the globe. For the largely pre-electrified world, the moment passes with minimal damage. That might not be the case today.
It has the potential of knocking out power grids. And if it burns out transformers that are hard to replace, we may be without electricity in many areas for a very long period of time. There's only a few places that make these 125 kilovolt transformers. It takes several months to make them. And if you burn out half of them, we're going to be shooting squirrels and chopping wood out the backyard for a long period of time just to survive.
Everything grows,
building up.
but the 3Ds really...
Today's solar scientists believe it's not if, but when the next big one will strike. With the next solar maximum due in 2013, it begs an all-important question. Can we predict when the next solar storm will hit?
No.
Maybe.
No.
Maybe.
No.
Maybe. And the reason why is we've learned so much about the sun. We're getting better at it, but we have a long way to go. And the more we look at some of these historic events, the more we get a deeper appreciation for what we need to know.
Today, we see the sun better than ever before. We're beginning to understand it from the inside out. But its unpredictable personality means there will always be uncertainty when living with a star.
In the quiet of a brisk October morning in 1960, liquid oxygen bathes a launch pad in an ominous fog. The Soviet Union is poised to take a giant leap ahead in the burgeoning space race. Deep in the steppes of Kazakhstan, hundreds of miles from civilization, and a world away from Western eyes, a powerful new rocket points skyward. 2 previous endeavors have failed. They are determined to make it work now, at any expense. The launch of Sputnik in 1957 had kicked off a feverish era of space exploration. While the Americans struggled with their Vanguard rockets, the Soviets sent a dog named Laika into orbit. Their Luna probes dazzled the world, hitting the moon in September of 1959, then taking photographs of the dark side a month later. The U.S. had successes with Explorer and Ranger, but the Soviets were clearly leading the pack, and by long strides. Even as the rocket readied for takeoff, Premier Nikita Khrushchev was in New York for a United Nations meeting, anxious to gloat about another Soviet success while on American soil. Back in Kazakhstan, the pressure was on to launch now, no matter what. During the countdown, a malfunction was discovered. Normally, this would result in a postponement, but not on this day. Fuel surged through the rocket boosters. Minutes later, the compound exploded into an inferno that would claim nearly 200 lives. The world was left with hearsay, rumor, and speculation. Until now. Unexplained deaths, harrowing encounters in space, phenomena that puzzled the world for decades. These are the files long hidden behind the impenetrable seal of the Iron Curtain. Today, we can finally explore those hidden vaults, bringing to light the darkest mysteries of the secret Russian space program. From the beginning, the Soviets and Americans amazed the world with their stellar achievements. But that glory has been marred by disaster. Time and time again, the deadly matrix of politics, human nature, and destiny has shattered the myth of technological perfection. While rocket power has boosted humanity to new heights, its searing flames remind us that in the perilous pursuit of outer space, false starts are often fatal. The environment of space is even less forgiving. The smallest miscalculation can boil blood in minutes, or leave a spacecraft and its passengers marooned in orbit as life slowly trickles away. 1967. In the hasty race to beat each other to the moon, someone was bound to make a mistake, a deadly one. The Americans would misstep with the fiery deaths of the Apollo 1 astronauts. Then the Soviets, in their rush to the moon, would follow with the first in-flight death of a cosmonaut. It wouldn't be their only taste of tragedy and regret. Violent explosions on the launch pad, fatal miscalculations, and crucial equipment failures. The margin between life and death can be harrowingly thin. Sometimes fate smiles. Other times, it turns a blind eye. True stories, like that of the Soviets' deadliest disaster, are finally being pieced together. The missile poised in the launch pad that pivotal day in October 1960 was the R-16 ICBM, the pet project of Mikhail Kuzmich Yangel. It was a rocket designed to deliver deadly nuclear warheads to the U.S. This would be Yangel's first test at a newly constructed launch pad at Baikonur, and it was scheduled for the anniversary of the Great October Revolution. Marshal Nijelin was the commander-in-chief of the Strategic Missile Forces. He would conduct the test himself. Many of the top military officers and rocket designers were there to watch the historic launch. But the launch was off to a disappointing start. An electrical problem threatened to abort the entire mission. Protocol demanded that technicians deactivate the boosters and drain the fuel. But that would mean weeks of delay. For Nijelin and the prestige this launch represented, failure was not an option. Sergei Khrushchev learned of the classified disaster from his father, former Premier Nikita Khrushchev.
But because they thought that they saved the marshal, who was the head of the commission, he took his chair and sit under the missile. And all other people gathered around the missile, which was full, which is crazy.
Indeed, Marshal Nijelin's confidence was in vain. As engineers tried to fix the problem, they accidentally triggered the ignition sequence.
The engine began to work. Of course, it was just burned the first stage, and 150 or 160 tons of all this stuff just dropped down, and it began the fire, and they burned everything there.
Within seconds, the pad was a towering inferno. What you are seeing is that actual disaster. 126 people died instantly, including Nijelin, charred beyond recognition. 50 more would die later from their injuries. The world's greatest single missile catastrophe. While burning victims tried and failed to make their way out of the raging inferno, others walked directly into its burning center. They weren't going in to save their comrades. What they were after was of much higher priority. They risked their lives to preserve this flaming box. What secrets that box contained may someday also come to light. Until that day, it remains yet another of the unexplained mysteries that comprise the Soviet space archives. Nothing in the known annals of space history matches the Nijelin catastrophe in terms of life lost. But it was hardly their only disaster. In 1969, the Soviets prepared to launch their second generation of Mars probes. The United States had edged ahead in the race to the moon, so a successful Mars launch would be an appropriate reply. These probes were to be carried by the powerful new Proton booster, which had 3 times the thrust of the earlier booster and 3 times the troubles. Though its designers gave it only a 50-50 chance of success, political forces deemed it worth the risk. None of the 3 launches were successful, but the attempt you are witnessing nearly turned fatal. Luckily, the rocket crashed on an uninhabited area of the base. This disaster was preserved on film. The legacies of countless others have evaporated as quickly as the smoke that swirled around their burning wreckage. Like the launch fire at Plesetsk in March 1980, which to this day remains shrouded in mystery. Film of the blast and fire were destroyed, and no photography was permitted at the funerals of those who died. For Alexander Kosuk, the experience is permanently seared into his memory. Half an hour before the launch, he descended these stairs to an underground bunker. The Soviets had been attempting to launch a spy satellite when an oxygen leak was discovered. Rather than follow safety procedure, an oily rag was used to temporarily stop the leak. It ignited almost immediately.
And at that time, there was a big blast. The bunker was full of flame and hot gas. Then another blast, a third one. So nearly all the people near the booster, the combat team, perished. 49 people altogether.
Whatever the flames didn't consume, the Soviets made sure to get rid of. They succeeded in destroying all evidence, but they could never erase the painful remembrance.
This can never be forgotten.
But how can these victims be remembered when they are not officially even a part of sanctioned history? This hushed policy of secrets and lies has its roots decades in the past. In the early 1960s, while the Americans were developing the Gemini two-man spacecraft, the Soviets were also developing their larger Soyuz spacecraft. But Khrushchev was anxious for more space firsts. Engineers quickly came up with the Voskhod spacecraft, and the Soviet need to top its rivals with space triumphs continued. Voskhod 1 would carry a crew of 3 into orbit. As Voskhod 1 landed, Leonid Brezhnev was hustling Khrushchev off the Soviet stage. But the space race continued. Soviet spacecraft Voskhod 2 was launched March 18, 1965. In the first spacewalk, cosmonaut Alexei Leonov took a step into the abyss while the world watched. What few people realized was that the first man to walk in space was almost the first one to die there. Yet another of the many shocking secrets newly liberated from the vaults of Soviet history. With the collapse of the Soviet Union, much of the previous deception of the Cold War era has vanished. Now, in order to sell their launch services on the open market, the former Soviet states are required to divulge their secrets, providing the world with detailed analysis of its failures as well as its successes. Some of the uncovered secrets date to the origins of the space race. Others, much to the world's surprise, happened after the Cold War. In a blow to Russian claims of reliability, 1996 resulted in 2 explosions of their most successful booster. Considered the workhorse of their program, the Soyuz U rocket had launched over 1,100 spacecraft. An investigation determined that both disasters were caused by defective parts. With sloppy mistakes such as these, it is easy to see why the newly independent Soviet nations, struggling to survive economically, would want to hide their failures. In the past, it was political motivation that turned truth into obscurity. With the opening of Soviet society, the world is learning about this hidden past. It is a history filled with failures and near misses, forgotten heroes and unknown cover-ups. Information that may have saved lives had it been revealed. In March of 1965, Alexei Leonov became the first man to walk in space. The world would revel in his success, but little would they know how close he came to ultimate failure. When Leonov returned to the spacecraft, he discovered an unforeseen problem. His spacesuit had ballooned more than expected. He couldn't bend his arms or legs. He floated helplessly, unable to maneuver his body back into the hatch. Dangling in the abyss, he began to panic. As his pulse and respiration soared, his body began to depressurize. He was soaked in sweat, his visor becoming foggy. He took a risk and lowered the pressure in the suit. This enabled him to squeeze through the airlock head first. He had barely survived with his life, and Leonov's terrifying odyssey wasn't over yet. On re-entry, the prime retro rocket system failed. Then, the navigation system malfunctioned, and the cosmonauts had to land manually. They landed 2,000 miles off course in the taiga forest of the Ural region. As day turned to night, the temperature plunged below zero. Wolves circled the men. They slept cramped in the capsule, huddled against freezing temperatures and the snarling creatures outside. Finally, after hours of misery, a ski patrol rescued them. In publicly recounting his spacewalk, Leonov put on a good show for the Soviet space program. He failed to mention the dire sequence of events that nearly cost him his life. His non-disclosure would be costly for Americans. Ambitious to match the Soviet achievement, NASA hurried to get its own astronauts walking in space. One of the first, Eugene Cernan, repeated the same harrowing experience that Leonov had, fighting for his life in a spacesuit that didn't function properly in the vacuum of space. It wasn't the first time that a lack of openness between space agencies had dire and even deadly consequences. Valentin Bondarenka was the youngest member of the first cosmonaut team. In March of 1961, he went into an isolation tank. For 10 days, he ate, slept, and worked in an environment of pure oxygen. The test went perfectly until the final day, when the young cosmonaut was wrapping up the experiment. Using an alcohol-dipped swab, he removed some sensors from his body. He tossed the swab towards the trash, but missed. An innocent slip-up would prove fatal. The swab had landed on the hot plate he'd used to prepare his meals. Flames exploded, consuming the pure oxygen and raging into a deadly inferno. For nearly 30 minutes, the cosmonaut was burned alive while rescuers struggled to open the sealed door. The charred body they finally pulled out was still alive, but barely. Dr. Vladimir Gulyakovsky was the doctor on call when Bondarenka was brought to the hospital.
He didn't have skin on his extremities and his body. He didn't have skin on his face. He didn't have hair. He didn't have eyes even, and lips also. So it was completely burned out person. Despite of this condition, he managed to talk, and I bent over to his face to be able to hear his voice. And was terrible smell, you know, it was difficult even to come closer to him. So I bent over his face and I heard that he said, "It's too much pain, do something, kill the pain."
The once vibrant cosmonaut was doomed, lingering for 16 hours in inconsolable pain and misery. The embarrassing incident was entombed along with its victim. Without the benefit of the Soviets' experience, the Americans would have to learn Bondarenka's tragic lesson firsthand. On January 27, 1967, the Apollo 1 crew, Gus Grissom, Ed White, and Roger Chaffee, entered their spacecraft for a pre-flight test. As was the case with Bondarenka, the capsule was pressurized and enriched with pure oxygen. And as Bondarenka, these astronauts would perish when this oxygen atmosphere turned a small spark into an all-consuming inferno. The accident report blamed shoddy wiring for causing the spark that started the fire, the flammability of materials, the oxygen-rich atmosphere that allowed the spark to become a holocaust, as well as the lack of a quick-release escape hatch. But what seemed unavoidable could have been averted if only the Americans had known what happened to Bondarenka. Despite their best efforts, the engineers at the helm of both space programs were operating in untested realms of experience. Devising contingency plans was as much the stuff of imagination as hard science. In such uncharted territory, death was often cheated by the thinnest of margins. Such was the case with two cosmonauts who would experience their own life and death drama. Gennady Strikalov and Vladimir Titov were ready for their mission. On September 26, 1983, about 90 seconds before Soyuz T-10A was to lift off, a malfunction resulted in a fuel spill which quickly ignited. An abort was commanded, but the communications lines had already been burnt through. As flames engulfed the booster, a backup radio command activated the abort sequence. The cosmonauts were a few seconds away from perishing in the conflagration. Here, as we see actual footage of this event, the escape system worked, and the capsule pulled away from the booster 6 seconds before it exploded in a ball of flaming death. In a perfect world, the tragedies of the past would provide us with lessons for the future. In a world where history is manipulated, there can be no such consolation. On January 28, 1986, the bleachers at Cape Canaveral were filled with excited onlookers, families, and friends. But their overflowing pride would do nothing to prevent the horror of what took place. A mid-air explosion that blasted the shuttle into pieces. Had the Americans been aware of the details of the near disaster aboard Soyuz T-10A just 2 years earlier, perhaps they wouldn't have been blinded by their self-confidence. Over 25 years after the Soviet Nedelin catastrophe, a space program was once again driven by political pressure, allowing the fatal consequences of haste to yet again martyr the exploration of space. Over the years, experience, safety precautions, and technology all combined to make spaceflight safer. But political pressure, human error, and cruel fate repeatedly made for a combustible and often tragic mixture. 1967 was a very anxious time for the Soviets. It had been 20 months since the last manned Voskhod flight, and the first manned launch of their new Soyuz program had still not yet occurred. During this period, the Americans flew 10 manned Gemini flights, successfully completing many maneuvers necessary for a lunar landing. But it was also the year that Apollo 1 burned on the launch pad, killing 3 astronauts and sending NASA back to the drawing boards. With a successful launch, the Soviet Union could boast the superiority of Soyuz over Apollo and regain the initiative in the race to the moon. The authorities wanted this new victory in time for the 50th anniversary of the Great October Revolution. There had been 4 unmanned test flights of the Soyuz re-entry vehicle, but none had been successful. In fact, each unmanned test had shown new problems. But as the gap between manned missions extended, political pressure for another Soviet space spectacular grew. And there was no one in the program with the authority to defy the Politburo. A spectacular space mission involving veteran cosmonauts was devised. 2 manned spacecraft, Soyuz 1 and 2, would be launched. They would perform an untried docking and crew transfer in space. Fanfare surrounded the pioneering project, but back at Mission Control, engineers were filled with dread. They simply weren't ready. Even the chief designer refused to certify the launch. Still, the Soyuz went to space. Piloting the ship was cosmonaut Vladimir Komarov. It wasn't long before the Soyuz 1 began to show the signs of malfunction that everyone on the ground dreaded. At the outset, one of the solar panels hadn't deployed. Then, the altitude control systems failed. Because of Soyuz 1's unreliable performance, Soyuz 2 was never launched. All efforts were put into the safe return of Soyuz 1. We know now that no matter how skillfully Komarov piloted the spacecraft, his fate had already been sealed. The Soyuz 1 was, the moment it rolled onto the launch pad, a death ship. Lurking silently within its belly was an untested parachute, a lifeline destined to fail. And aboard the Soyuz 1, a cosmonaut was fated to die. Nothing could save the doomed ship as it fell, end over end, towards Earth. From the top of the atmosphere, the capsule plummeted. Komarov impacted the ground at over 300 miles per hour. At the height of the moon race, news of such gross negligence could not get out, and so Komarov's story was buried along with his mangled corpse. And meanwhile, the world, blind to the death and disaster that had come before, celebrated the successes with enthusiasm. On July 23, 1969, when Neil Armstrong made that small step for man, the Americans made a giant leap in the seesaw race to the moon by crossing the finish line first. Ever the experts at propaganda, the Soviets feigned disinterest. They didn't televise the moon landing and barely covered it in print. They immediately denied that they ever intended to send a manned flight to the moon and proclaimed that they were turning their energies toward their space station program, Salyut, a program that would ensure a string of firsts, as the Americans had no such programs. Salyut was the first orbital laboratory in the world with the capability of long space flights. It was a plum assignment for a young cosmonaut named Pyotr Koloidin and his crewmates Alexei Leonov and Valery Kubasov. But fate had different plans. 2 days before the launch, the primary crew had their last medical test. A dark spot showed up on Kubasov's lung, and the Flight Commission replaced him with a backup. When Koloidin and Leonov were overheard lamenting the substitution of their comrade, they too were replaced, a seeming injustice, but one that would save their lives. And so in June 1971, Soyuz 11 took off without them. The craft completed the first successful docking with an orbital laboratory, and cosmonauts Viktor Patsayev, Georgy Dobrovolsky, and Vladislav Volkov spent nearly 3 weeks aboard the Salyut 1. But not all went smoothly. What you're about to hear is a real emergency in space, a chilling encounter with death too distressing to be revealed until now.
Прочтение вам по программе на 3 витка последних, а потом поговорим, ладно?
Ох, елки зеленые, что-то у нас целый день сегодня одними уточнениями пичкаешь.
Янтарь, примите форму 23.
Подожди, нам сейчас не до этого, у нас пахнет на борту горелым чем-то.
Понял вас? Сообщайте.
Что сообщать, пахнет? Янтарь 3 на связи.
Слушаю вас.
А что слушать, тут не поймем, откуда дым идет. Разбираемся.
Дым идет уже?
Да, идет. Но тут закрыты наглухо панели, не можем добраться быстро. Сейчас возьмем отвертки, будем вертеть. Тут сотни-две винтов.
Понял. Янтарь 2, выключайте всю ненужную аппаратуру.
Так это понятно, ты понимаешь, мы не знаем, что горит. Может быть, кабель горит, но его в жгуте не можем проверить. Понимаешь? Запах идет из-под приборной доски. Мы вскрыли панель приборной доски. Под ней обгоревший кабель в жгуте. И запах продолжает идти.
Если вы будете переходить в НКТ и делать расстыковку, то расстыковка штатная, завершающая операцию только по нашему указанию.
Леха, подожди. Нам некогда здесь будет соображать, если дело дойдет до серьезного. Я тебе задаю вопрос. Если здесь создастся ситуация, которая для нас опасна, мы заходим в океан, закрываем люк. Закрываете перед собой люк. Поняли, но мы так, эти сутки. В общем, по нашим данным, у вас все...
It seemed the danger had passed. The world sighed in relief. During their 3 weeks in space, the Soviet Union had given the mission extensive media coverage. The Salyut program was painted as much more challenging than the Apollo moon landings. A triumphant return was planned. As they neared the Earth's atmosphere, the cosmonauts fired off a series of rockets that would separate their return capsule from the rest of the module. But there was a glitch in the procedure. The force of the explosive bolts caused a valve to jerk open, rapidly sucking the air out of their cabin and turning their haven into a deadly vacuum. The cosmonauts hadn't been issued pressurized spacesuits because the craft was too small. One can only imagine the terror inside the capsule as they realized they had only 20 seconds worth of life left. When they arrived at the spacecraft, the stunned recovery crew hoped that the cosmonauts were simply unconscious. This dramatic footage shows their futile attempts at resuscitating them. The violent re-entry had caused their blood to boil for over 10 minutes. While the nation honored its martyred heroes with a memorial on the Kremlin wall, cosmonaut Kaloydin was burdened with a deeper grief.
I thought that I was somewhat guilty for his death, but Volkov was doomed in any scenario. And now I don't worry anymore, because I understand then I could do nothing.
Death knows nothing of geography or politics. The annals of space history are filled with the names of those who gave their lives to push the envelope of man's domain. Fortunately, not all the stories end in tragedy. Fate still manages to smile upon those seeking out the mysteries of space, even when the odds seem stacked against them. Space is an unforgiving dominion. Hurling through the barren vacuum, there is no lifeline, no safety net, and little room for error. Perhaps the most dramatic example of a space rescue remains the U.S. Apollo 13 flight.
Okay, Houston, we've had a problem here.
Once in orbit, emergencies haunted the crew of this April 1970 flight from the moment an onboard liquid oxygen tank exploded. After a treacherous journey back toward Earth, Apollo 13 re-entered the atmosphere, not knowing if their protective heat shield would keep them from literally roasting to death in the 6,000-degree re-entry. And if they did make it that far, they couldn't know whether their parachutes would even deploy. Tense moments passed as they re-entered Earth's atmosphere and went out of communications range. On Earth, all ears strained to hear sounds of life as Apollo regained radio contact. This time, fate was gracious. The Soviet version of Apollo 13 launched on April 10, 1979. The Soyuz 33 mission was the fourth international flight, whose crew included a Bulgarian cosmonaut. All was going routinely as they were preparing to rendezvous with Salyut 6. Then, on the Soyuz, something went dreadfully wrong. The tension grew as Mission Control consulted with cosmonauts already on board the station, waiting to greet the Soyuz crew.
Протоны, протоны. Вы видите пламя из двигателей Сатурна? Вы видите пламя?
Это было не как всегда. Это двигалось в сторону.
Вы видите это отчетливо?
Да, я уверен.
The Salyut crew had confirmed the unthinkable. For the first time in roughly 2,000 firings, the Soyuz main rocket engine had failed. It was the third mission for cosmonaut Nikolai Rukavishnikov, and definitely the most perilous.
We had an explosion at the rear engine of our Soyuz 33 ship. We could not dock with the station. Furthermore, we could barely return from orbit. It was a critical situation, and we had a good chance of not returning to Earth.
While Mission Control struggled for some way of bringing the ship home, Rukavishnikov realized the nightmarish possibility of being marooned in space with only 5 days of supplies. The crew would have to use their reserve engine for an emergency landing, but there was no way of knowing if it still worked without trying it. Mission Control ordered Soyuz to fire their backup engine. No one had to tell the crew what would happen if it didn't work up to capacity. The cosmonauts were already picturing that dreadful scenario. If the engine worked less than 90 seconds, Soyuz 33 would remain a live satellite for 5 days, then become just a satellite containing corpses. The reserve engine worked. It would mean they'd have to return to Earth at a steep trajectory and withstand a painful 10 Gs. But they would return to Earth alive. It wasn't the first time a Soyuz spacecraft nearly became a ship of death. On April 5, 1975, Soyuz 18A was intended to dock with the Salyut 4 space station. The flight never made it into orbit. The A2 booster malfunctioned, and the rocket began to deviate from the planned altitude.
During the launch of the spacecraft, we got a message from the cosmonauts. Accident! Accident with the booster!
The Soyuz fired its engines in a retroburn. Like Soyuz 33, they would return to Earth in a ballistic trajectory, but this time with double the agonizing pressure, a bone-crushing 20 Gs.
We had no possibility to get out of the capsule as we were taught. If we opened the hatch, which was underwater, there would be no chance to get out. Besides, the temperature on Tengiz was minus 22 degrees centigrade.
Now the cosmonauts faced real danger. With the capsule upside down, the valve connecting to the outside atmosphere was submerged. They had no way to get fresh air. They had to use the regeneration system to supply oxygen, but they were running low on power.
To stay in such a situation in the spacesuits and do nothing, we would freeze to death. We started to save electric power. We switched off all sources inside the capsule. Left on only the beacon and radio that we would need to use. But they soon failed.
Valery Rozdesvinsky feared the worst as the cosmonauts slipped in and out of reality.
You could feel the CO2 without instrumentation. Just feel it. When I felt close to losing consciousness, then I would switch on the regeneration. Then, when my mind started to clear and the blue haze disappeared from my eyes, I'd switch it off, and so on, all through the night.
9 hours after the landing, helicopters were able to locate the craft. Frogmen attached flotation aids and a tow line to it. As we see in these rare photos of the actual rescue, the helicopter couldn't lift the capsule, but was able to drag it 8 kilometers to shore. This time, death was cheated by the slimmest of margins. Though countless advances have made Earth's orbit seem more accommodating now, near misses like the Mir collision and decompression on June 25, 1997, are reminders that space is still a dangerous place. When American astronaut C. Michael Foale replaced astronaut Jerry Linenger aboard the Mir, NASA hoped that the worst of the near disasters were over. Lininger had endured a near collision with a cargo ship, as well as an ongoing litany of mechanical and electrical breakdowns, including an intense fire.
The fire was basically in this region here, with the flame shooting across this way. And therefore, as you can see where the camera is basically where I was at, and we had one other body in front of me. I was passing the fire extinguisher. At that time, the other Soyuz was on the other side where Progress is now docked. So as you can see, it would have been very difficult to get through the flame itself to get to one of the rescue vehicles.
Foale was to fare worse. Mission Control wanted to attempt a manual docking with a Progress cargo vehicle. Because of previous problems with the docking system, they decided to attempt the hookup with the radar system off. In Soviet tradition, human error was blamed for what would happen next. But as the facts have emerged, it's become apparent that the Mir was a victim of faulty planning. The crew nearly paid for these mistakes with their lives. The cosmonauts had practiced this manual docking maneuver before, but only with an empty cargo ship. This one was heavy and approaching fast. But without the main radar system, there was no way to know how fast or how far away it was at any given time. This lack of crucial information would nearly prove fatal. Cosmonaut Vasily Sabliev tried to slow the capsule with the braking lever, but the Progress kept coming. From the porthole, cosmonaut Alexander Lasutkin watched the Progress fly over the docking port.
I asked the technicians, how do you see the side of the station? By radar or on the screen? They replied, but nothing is on the screen. By radar, of course. So if we had radar, there would be nothing to talk about.
As Lasutkin ordered Foale to the Soyuz vehicle for evacuation, Progress crashed into Mir. The entire space station shook. The master alarm began to blare. The collision had caused an air leak. The life-sustaining atmosphere of the Mir was being sucked into the vacuum of space. The quick-thinking crew was able to save the station by severing a series of power cords so that they could seal off the damaged area. Mir survived the first decompression of an orbiting spacecraft. A split second later, a slightly larger impact, or a different course of action, and it all might have ended there for Mir and the men on board. The Mir collision has become legendary in space history. But had fate not smiled on them that day, their account might have been concealed, distorted, or forgotten, like so many of the stories before them. Today, the murky depths of the Soviet space archive are just beginning to divulge their secrets. Some of them so bizarre, so irrational, they seem fated to remain forever a puzzle. But other newly liberated files are answering questions, explaining the great mysteries of space, and filling the void with a rich, colorful human history.